As mentioned earlier, if I have a mass going in a circle of radius r, its moment of inertia or rotational inertia is just mr squared. Now, what about more intricate shapes? For example, if we take a cylinder and we get it to spin about its center. Now, if it is spinning about its central axis, then its moment of inertia is given by 1/2 of mr squared. There is a way of calculating that. It uses calculus, what we call integration in calculus. But we are not getting into that. Usually, for simple shapes, you find tables in books, in websites that give you the moment of inertia relative to some special axis. Like in this case, when we have a solid cylinder, solid means it's full of mass throughout, about its central axis, then we can get something like this. Now, however, if all the mass is around the outside of that cylinder, like in here, and we are still rotating it about its center, then the moment of inertia is just mr squared. You see, it's a higher moment of inertia than the moment of inertia here. This one is 1/2 of mr squared, here it's mr squared. Now, this equation is very similar to the equation for moment of inertia when we had just one mass going in a circle. Now, what if the mass is not fully distributed a distance r away? What if it is distributed between a distance r2 and r1, like here? Then it gets a little more trickier. It's 1/2 of m r1 plus r2 squared. Okay, in here, for this particular course, I'm just showing you these so you can see the complexity of how we get moment of inertia. We are not going to spend time trying to figure out moments of inertia for different shaped objects. We will just stick to the main principle. I'll show you a few more shapes. Like here, we have a rectangle and we are getting it to rotate about the center. In this case, it's 1/12 of m a squared plus b squared, where a and b are the sides. Of course, if it was a square, it's going to be a squared plus a squared, so twice a squared, so it's going to be 1/6 of ma squared. Now, what about a solid sphere, like a bowling ball? That's 2/5 of mr squared. Of course, if it is like a basketball where all the mass is distributed around the outside, that's the key point to remember. When the mass is further away from the axis, then we get a higher moment of inertia. Like here is 2/3 of mr squared as opposed to 2/5. 2/3 is larger than 2/5, of course. Let's look at this other example. We have a stick. Remember, we talked about a stick rotating about its central axis. Now here, it's rotating about an axis that's perpendicular to the stick. The length of the stick is L. It's rotating about this axis. Moment of inertia is 1/12 of ml squared. This is very much like the stick that the little girls in the video were rotating about the central axis here. What if we rotate it about the end? Like when the gentleman from Louisiana was trying to balance a stick. Then the moment of inertia, because I have more mass further away from the axis, is going to be higher. And it's 1/3 of ml squared as opposed to 1/12 of ml squared here.